Hey everybody, we're going to continue talking about our real zeros of our polynomial functions, and this time we are going to be using the rational zeros theorem to list the possible zeros, technically the rational zeros of our polynomial functions. So last time we talked about Descartes' rule of signs, and before that we were learning about the remainder and factor theorems. So the rational zeros theorem says the following: if we have a polynomial function that looks like this, just in general, then where each coefficient is an integer, that's part of what's required, we have the following: p over q, if that's in lowest terms as a fraction, it's a rational zero of our function. And that's if p is a factor of a sub 0 and q is a factor of a sub n. So let me rephrase this so that it's a lot more clear. If you take your polynomial function, notice where a sub 0 is, it's the constant term in the end. So if this is the very last term and there's no x with it, this is just your constant term, and you take your a sub n, which is in the very front of your polynomial and it's on the highest degree of x, this one is going to be what's called your leading coefficient. So this theorem says that you have rational zeros. Okay, so first let's clarify that rational numbers are just numbers that can be written in this form, like a fraction of integers. The top is an integer, the bottom is an integer. So you have rational zeros, where the zeros, the rational zeros, come from this list of numbers. So your possible rational zeros, let me add the word possible here, because this is a list where you can choose from, but not all these numbers are going to actually be your zeros. Your possible rational zeros come from this form. They come from taking the factors of the constant term. So factors of the constant term, which was a sub 0 right here in the back, and dividing them by the factors of the leading coefficient of your polynomial. Leading coefficient. Let me just abbreviate that. This one here. So all you do, and we'll do an example, is you find your last number, your constant, you find all of its factors, and then you take your leading coefficient and find all of those factors, and you divide. And then you make a list of numbers. And then that list, and everything on that list, is where you might find your rational zeros for your polynomial function. Okay, so let's work that out. So list the possible rational zeros of this polynomial. So as a quick reminder, a zero, a real zero of a function, let me clarify, this is not the number 0. A real zero of a function means when you plug it in, the answer is 0. So what we are looking for is we're looking for all the numbers that when we plug them in, we get 0 out of our function. But that could be a lot of numbers that we could randomly try. So instead of randomly picking numbers, we want to find a list that gives us just a few numbers to try. And so the possible rational zeros come from the whole process we just talked about. Okay, so first of all, we can use the theorem because all the coefficients on these terms are integers. And so let's list the factors. Okay, so we have a constant of 4. So we want to list the factors of 4. And we have a leading coefficient of 2. And we want to list those factors as well. Okay, so the factors of the constant, so constant term, constant factors are going to be 1 goes into 4. So think about what multiply to make 4. 1 times 4 and 2 times 2. So your factors are 1, 2, and 4, but positive and negative, because negative 1 times negative 4 is also 4, and negative 2 times negative 2 is also 4. So the list usually gets condensed like this, but just know that this can expand as negative 4, negative 2, negative 1, 1, 2, and 4. So this list has 6 numbers on it so far. And then we want to take the factors of the leading coefficient, so the leading coefficient factors. So those are going to be the factors of 2. And the only way to get 2 is 1 times 2, or negative 1 times negative 2. So that list, if you expand it, looks like negative 2, negative 1, 1, and 2. So this list has 4 numbers on it. And what the theorem says is that you take the factors from the constant and you divide them by the factors of the leading coefficient. So we're going to take the numbers from the first list, divide them by the numbers from the second list. Alright, so the factors from the first list divided by the factors from the second list. And you have to just kind of write this out, and you can, I would just try to stay organized, but if you recall, the factors from the bottom, the factors from Q, and or our leading coefficient, were positive and negative 1, positive and negative 2. And so you're just taking all the factors from the numerator, which was positive and negative 1, 2, and 4, and you're making a list by dividing them by the denominator. So let's just write that out really quick, what happened here. So we have, if I expand this, let me go ahead and write this the long way. When you get comfortable with it, you don't have to write this out, but I want to just show you exactly what happened. So this is really what we had. This is our list from our numerator, and we want to take all of those numbers and divide them by all of the numbers in the denominator. So we want to divide them all by negative 1, and then we want to divide all of those numbers again by positive 1, and then we want to take all those numbers and divide them by negative 2. So again, I'm just doing this a long way to show you what's happening, and then all those numbers and divide them by positive 2. So really what we're doing is we're doing 4 different things, and so that's why we condense the notation with the plus and minus signs. And so when you start simplifying, let me go ahead and erase some of this so it's not so ugly. We'll start with the 1s. Okay, so think about what happened here. And as long as you put the plus and minus in the front, you can shorten your work. So when you take your numbers and you divide them all by 1, it's the same list of numbers, right? So we just have negative and positive 4, negative and positive 2, negative and positive 1. So that's these ones here. Negative and positive 4, negative and positive 2, negative and positive 1. Then if I take all my numbers and I divide them by 2, let's go ahead and do that again really quick. Then I have negative and positive, let's go here, negative and positive 2, which is already on my list. That's these ones. I'll cross them out. If I divide here, this is going to be negative 1 and positive 1, which is already on my list. Cross that out. And then divided by 2, this is negative and positive 1/2. So that's the rest of my list. So this list has 8 numbers on it. Let's write it out the long way. Negative 4, negative 2, negative 1, negative 1/2, positive 1/2, 1, 2, and 4. Okay, so that is how you list the possible rational zeros. And so what this means is that for my polynomial function that I started with, if I have any rational zeros in that function, they're on this list. So the function was degree 5, so there's not 8 zeros, but what this list is saying is that if any of my zeros are rational numbers, they are on this list. And so in the next video, we'll start working at examples to where we will use this list along with Descartes' rule of signs to figure out which numbers from this list actually plug back into my function. I plug those numbers into the function and equal 0 because that's what makes them a real zero. Okay, thanks for watching.